Great. I'm very happy to introduce Cynthia Dwork, who, according to Wikipedia, is an American computer scientist, and Gordon Mackay Professor and Radcliffe Alumni Professor at Harvard. She's done a lot of foundational work in distributed computing and cryptography, and a bit in differential privacy as well. And today she's going to tell us about the relationship between group and individual notions of algorithmic fairness.
Thank you for the introduction. Thank you, organizers, who, when you invited me to speak, I said, well, I'll probably want to talk about fairness. Is that okay? And they said yes. And I've been thinking about some of these things for a long time, and I hadn't really forced myself to try to pull the threads together. So this talk is the first attempt to do so, and it was gratifying. So anyway, I appreciate that. Okay, so many of you have seen a slide that looks a lot like this already. I'm not going to belabor the point. We're talking about algorithmic fairness. We have a population that's very diverse, and the concern somehow is that different groups are treated differently in an inappropriate way. Now, sort of following the classical paradigm from cryptography, the approach that we tried to follow when we started this work back in the summer of 2010 was to first define what we mean by fairness, then find algorithms that give us fairness, and ultimately then we were going to look for composition theorems, so just the kinds of stuff that you've been seeing here too. So the definitions of fairness that are in the literature basically fit into two categories. The group notion. Group notions are essentially statistical requirements about the way pairs of groups are treated. So the classical example that's really easy to understand is statistical parity. If you're admitting students to a university and you have a well-defined notion of what your population is, then the fraction of admitted students that belong to the minority group should be the same as the fraction of the minority in the population as a whole. That is a statistical parity. And there are a number of difficulties with statistical parity, and so even early on we rejected it in general as a fairness notion. So then we looked at a different approach, which we call, I should mention, sorry. Despite this, almost all of the very large literature on algorithmic fairness deals with some form of group fairness definition. They do not deal with what I'm going to describe next, which is individual fairness. Individual fairness intuitively says that for looking at classification, for example, for a given classification task, two people who are similar with respect to that particular classification task should be treated similarly by your classifier. And the difficulty with this approach is that it requires a task-specific metric for determining for this task how similar a pair of individuals is. So that was really problematic, and that sort of stopped for a while, which probably explains why all of the literature more or less is about the group fairness notions. But there's been a really nice breakthrough, or I think a very intriguing breakthrough by Ilvento, where she looks at building a metric, learning a metric from a human judge or an oracle. And it's an interesting mixture of sort of learning theory and insights from human-computer interaction. And it seems that there are certain types of questions that humans find very difficult. For example, how different are these two people? And there are others that people find much easier. So given A, B, and C, which of B and C is more similar to A? That's a simple query. So she manages to build a metric or some nice approximation of a metric with very, very few difficult queries and on the order of n log n easy queries. Okay, and then there were other works that looked at specific questions under various conditions for in the individual fairness model, and that were really intriguing, but I'm not going to get into them today. Okay. Now, while I said that the group notions fail under scrutiny, there is at least some opinion in some legal scholars that certain of these notions are appropriate in certain contexts. But the individual fairness has a very strong legal foundation. That is, the idea that what is said, similarly situated people should be treated similarly, is absolutely pervasive in law. But of course, that still begs the question of, or no, not, it poses the question of who is similarly situated to whom. And just to give you a flavor of some of the issues that will come up, there's this question of if you're trying to build a metric, what should the metric capture? So sort of taking standard cryptographic practice, I'm going to assume that I have a person X, and X has internal randomness, and X interacts with an environment, for example, the workplace environment, and there's randomness in the workplace environment. And then we have a well-defined, if difficult to measure, probability, pi x, which would be the probability over the randomness in X and in the environment, that X will succeed at, say, the Nice News company. So this is a company where people are treated well and everybody can sort of reach his or her own potential. And success maybe is defined as staying at the company for at least 3 years and having at least one promotion during that time. So intuitively, what we would want then is that if pi x and pi y are close, then x and y should be treated similarly, should have a similar chance of getting hired. But we could be at a different company, which is, say, hostile to women, so the Nasty News company. And now, well, the chance that the woman will succeed, meaning that she'll stay there for at least 3 years and have at least one promotion, even if she's equally talented and qualified for the job, may be decreased because the environment is hostile to women. So what should the metric be capturing? The story at Nice News or the story at Nasty News, or what? Now, I also got you all to accept really easily this notion of probability. I said, okay, well, we've got randomness in the person and randomness. But when I talk to people outside our filter bubble of the crypto community, they say, what? What are you talking about? This isn't a probability. Anyway, before I get into that, we could say that pi x somehow is measuring the strength of x's qualifications, or maybe the degree of ability, where in actually trying to assess ability, we might factor in stereotype threat. So what is stereotype threat? Stereotype threat is a tendency to underperform in conformance with a stereotype that expects one's group to underperform. So before you all jump off to SATs, one of my favorite examples of this is an experiment involving golf. And I can't remember whether it was a miniature golf course or a real golf course. But there's a stereotype that white men are not good at sports and black men are good at sports. And if you tell white men who are now going to swing this golf club and hit the golf ball that they're being tested on their sports ability, they do decidedly worse than if you tell them, I don't know, something that's very, very neutral. Whereas if you tell black men that they are being tested on their sports ability, it has absolutely no impact. So the stereotype threat is affecting the white men in that scenario. And stereotype threat has been measured in lots and lots of settings. So when you're comparing somebody's qualifications, now let's go back to the SAT scores or the math test scores or whatever, it's interesting to maybe you should factor in stereotype threat. Okay, so anyway, all of these are sort of involved in what should the metric capture. Now, so as I indicated, this question of the individual probability is very elusive. So just to focus on a couple of scenarios, what's the probability that a person P will repay a loan? So when you think about that, how do you possibly measure it? And this is not a repeatable experiment. You're not going to give them the loan, see what happens, give them the loan, see what happens, and so on. There's no rewinding like there are in proofs of zero knowledge. So what do? Well, most people would start to say, well, we think about people who are similar to P. Well, what's the right notion of being similar to P? We're sort of back where we started from. And you also see perhaps that the features that you use to determine who might be similar to P will become a vector for introducing bias. So you have to be very, very careful. Other kinds of scenarios, there's a tumor. What's the probability that this tumor will metastasize under a certain course of treatment? Or a really well-studied problem in the statistics literature is forecasting. So you have a forecaster who, now this is a sequential version of the problem, every day is predicting what's the probability that it will rain tomorrow. What does that mean, the probability that it will rain tomorrow? We can't rerun tomorrow. So what's this collection that we're looking at to get our probability? And most poignantly, of course, are questions like, when you're using predictive instruments to determine whether somebody will go to jail or not, and you're asking, what is the probability that this particular felon is going to recidivate, is going to commit another crime in the next 2 years, or a violent crime in the next 2 years? So these are old questions. This is a paper published in 2018 by Philip David, who had clearly been thinking about these things since the early 80s. And just look a little bit at what the abstract says. We survey a variety of possible explications of the term individual risk. He was, in fact, I think, motivated to go back over all of these things because of the use of recidivism prediction instruments in the court. These, in turn, are based on a variety of interpretations of probability, including classical, enumerative, frequency, formal, metaphysical, personal, propensity, chance, and logical conceptions of probability. And later it says, although in the end the concept remains subtle and elusive, some pragmatic suggestions for progress are made. So this is an old question, even in the statistics literature, among people who really, really look at these things. And by the way, I should mention that what I keep in mind when I'm thinking about all of this is, what if I were an expert witness in court asked to explain the meaning of a recidivism risk score? What would I say, and why would I be satisfied with what I've said? So I think, as a community, the people who look at algorithmic fairness have to have a good answer to these questions. Okay. So I just want to mention that the probability question is sort of germane even without regard to fairness, as we've seen in forecasting, for example. And another way of thinking about this is maybe to say that, in some sense, accuracy, because that's what we're trying to get at with individual risk or individual probabilities. We can think of accuracy as a first step in ensuring fairness. It's like, first we try to figure out what the situation is, and then we want to figure out how to deal with it and make it fair. Okay, so I said this was old in the statistics literature. Here are a couple other places it comes up. This is Ernest Burgess, who wrote, "Predictability is feasible." He created a parole prediction instrument comprising a 21-factor test to determine, based on group recidivism rates, the likelihood of success or failure of any inmate eligible for parole. That was 1928. And in fact, the penologists really got into this, and they built all of these categories. And you know, you start to think that everything is going to be clear and objective and so on, but they degenerate into category names like ne'er-do-well and drunkard. And so, okay. One way of thinking about these things is, in the words of Bernard Harcourt, whom we'll see again in a moment, the use of, and he's deliberately twisting language from the insurance industry, the use of statistical rather than clinical methods on large data sets to determine different levels of criminal offending associated with one or more group traits in order, 1, to predict past, present, or future criminal behavior, and 2, to administer a criminal justice outcome. Some of my favorite writing on this topic is in an article by Barbara Underwood, who's she's the, I think, current Solicitor General of the state of New York. So in 1979, so long before the big AI revolution, first of all, in talking about, I went over this too fast, clinical versus actuarial judgments. So actuarial judgments are basically these predictive instruments, or literally actuarial tables, or the kind of thing that Burgess was building. Clinical judgments literally think about the psychologist examining the prisoner and trying to make a prediction of recidivism risk based on this detailed one-on-one interaction. So the clinician, brings to the table lots of experience with other patients and so on, but is not, in this scenario, using statistical tables, okay? So Underwood phrases it really beautifully. She says the distinction between clinical and actuarial describes 2 different ways of approaching the task of moving from evidence to facts. And that task presents similar problems whether the facts to be found are past or future. So we've been thinking about this as prediction, which is future. But in a courtroom, can we actually start seeing these things applying to the past? Let's figure out what probably happened. And there's a little bit of this in the preponderance of the evidence, the majority of the evidence thinking. So, okay. So I thought that was a beautiful way of framing it. Now, I mentioned a psychologist for the clinical judgments. The psychologists certainly have been thinking about this. And in 1954, Paul Meehl published his book, Clinical versus Statistical Prediction. He comes down pretty heavily in favor of statistical prediction. And he says, essentially, we think that experienced people make really good judgments. They don't. Right? And he has a bunch of studies in which he shows this, but of course, we have to see which statistical stories was he including as their selection bias in his comparison set. I don't know the literature well enough to answer that question. I've seen some of the lawyers write about this. I should mention that for everything that I'm telling you about, I did read the papers, except I couldn't read Meehl's book. It was just filled with references to schools of psychological thought and belief systems that were completely foreign to me. And as Martha Minow put it, it was like being parachuted down into the middle of an argument. You just have no idea what's going on. Okay, so Barbara Underwood wrote that maybe this distinction, well, it has sometimes been argued that the dichotomy between methods of prediction is false because clinical methods are simply inchoate and inarticulate forms of statistical decision making. So, in other words, the clinician is generalizing from past experiences. That's a set of experiences, and it's another, right? But then she points out that the argument misses a critical distinction. A clinical decision maker is not committed in advance of decision to the factors that will be considered and the rule for combining them. And I think that's a really important point that our literature needs to explore further. I want to go into that further. So, in other words, the clinician is adaptive. Now, remember, she was writing in 1979. She did not anticipate deep learning. And so she was somewhat attracted to actuarial methods because you're giving your method, and the method can then be examined to see, is it using race, is it using gender, and so on, in an inappropriate way. As I say, this did not anticipate things that would be created by deep learning where you simply have no understanding of what the features are. And of course, we also know that it's a whole lot more subtle than people realized anyway, even when it looks simple. But I think that just, yeah, okay. Now, Friedrich Schauer takes the position that, as we said earlier, all clinical judgments are generalizations. And his view is, you're going to stereotype, it's okay, get over it, profile, use profiling, but be careful and be ethical. And he has some really fun examples in his book about how this kind of reasoning is viewed in court and how it doesn't yet work. So he gives the example of the so-called blue bus company, where, very roughly speaking, there's an accident. A car was hit by a bus, and say 80% of the buses in town are owned by the blue bus company and 20% by the green bus company. So obviously, the preponderance of the evidence is it was probably a blue bus. Is that a reasonable way of deciding the outcome? Or another example, you've sold a large number, you have a stadium. It's packed. But it turns out that when you look at the ticket receipts, you only have the ticket receipts for just less than half the capacity of the stadium. So now, for any given person, the probability that a randomly chosen person was a gate crasher is more than a half. Preponderance of the evidence. So can you sort of charge them all with gate crashing? Okay. So anyway, Schauer is sort of in favor of permitting profiling and stereotyping. Harcourt is against it, and he has a book, Against Prediction. And he makes some really interesting points, which, from a computer science perspective, makes sense. So he says, hey, the criminal population is not working on static rules. When they see how you are profiling, the way in which criminal behavior is distributed is going to change. And he gives in the introduction to his book as an example, if it's known that the police are profiling black drivers, then the black drivers may in fact stop carrying drugs, but the white drivers will up their drug carrying because they know they're not going to be examined. So, and then he points out other evils, like, but I don't want to go into it now. Okay, great. So that's Harcourt. Now, interestingly, he proposes randomization as a solution. So he says, for example, that in the policing realm, you should, say, randomly sample IRS filings for audits, or use some sort of random sampling on the license plate numbers for consensual searches. In sentencing, he's very against using predictive devices. Okay, great. We're almost done with the background. Sonia Starr points out that, in a Stanford Law Review article, points out that basing criminal sentences on actuarial recidivism risk prediction instruments that include demographic and socioeconomic variables violates the Equal Protection Clause and is bad policy. It's an explicit embrace of otherwise condemned discrimination, sanitized by scientific language. However, I don't think that this has been, let me just check my notes and make sure I've got this right. Her argument has not been accepted by a court, and it depends on impact analysis, which the current Supreme Court does not like. All right. Now, closer to home, there's a really, really interesting NBER article by Kleinberg et al., where they're trying to look at the behavior of judges versus algorithms. And what they find is that an algorithm is more effective than judges. And so here, a policy simulation shows crime can be reduced by up to 24.8% with no change in the jailing rates. Or you could flip it around, and jail populations can be reduced with no increase in crime rates if you were to use the algorithms instead of the judges. Now you have to wonder, how do you deal with counterfactuals when, and they do really beautiful things to address that. So I highly recommend the paper just for the joy of seeing some of these techniques. Okay, so basically they support Neal. They're saying that, we may think that the judges are wise, but they're not. The algorithm is wiser. Okay. So let's get back to individual probabilities. We talked about this a little bit. So let's talk about the tumor. So here, I'm sorry. Did I go through this list? Yes, I did. I'm sorry. So here's the tumor. I've got this tumor. And a study that looks at certain aspects of the tumor, maybe certain parts in its DNA, says that 40% of these will metastasize. By the way, when I spoke to radiologists about this, she immediately got distracted by the numbers. That's a huge number. Forget about that. It's just a made-up number. So anyway, okay, so you do a study. It says that 40% are going to metastasize. Maybe there is a second study. And the second study also shows 40%. And the second study is measuring other features. What should you conclude? Should you conclude that, in fact, it's going to be 40%? Should you say, oh, you've got two sets of risk factors. This is terrible. The chance is going to go way up. Who knows? You can't tell, given just these estimates, what is the right belief about this particular tumor. And I don't use belief in a knowing way. I'm not talking about Bayesian anything. I'm just you just don't know what to make of it. Okay, and what if you have two different studies that show different numbers? What should you think? Should your prediction now go up? If before you were going to say, okay, well, everybody's saying 40, I'll say 0.4, I'll say 0.4, so. Okay, so this seems to be related to or at least some days, I think this is related to a more classical problem of combining the opinions of experts. And so you can think of an expert as somebody who really shares all of your values and beliefs and knows something more than you do. For example, the results of a study. In which case, if you knew what the expert knew, you would change your belief to whatever the expert believes, because they think the way you do and they just have more information. So here we've got two different experts. They know two different things, the results of two different studies. So perhaps you might hope that the literature on combining the opinions of experts can help. I found that very inconclusive, but I don't rule it out completely. Now, in the weather forecasting literature, they define the notion of calibration. Maybe it was defined before that, but this is where I first saw it. So remember that this is, what's the chance that it's going to rain tomorrow? So your forecaster, imagine, is just forecasting day after day after day after day and is producing some probabilities. I listed them here: V double prime, V, V prime, V, V double prime, V, 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 blah, 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 U, W, and so on. So calibration says if we look at all of the predictions that say V, all of the days where they said V, then on a V fraction of those days, it should have rained. The fraction of days, so in other words, on average, the V predictions are correct. And the W predictions are correct on average. So for every value of V, if you look at the days where V is predicted, then a V fraction of them will have had rain. And I think usually these things are defined in terms of infinite sequences. There are some finite sample analogs in the literature. Okay? And it's often viewed as the sine qua non of forecasting. If your forecaster, the literature is filled with comments along the lines of, if your forecaster doesn't do this, something's wrong with your forecaster. And you might say, well, maybe my forecaster consistently underestimates. Well, an infinite forecaster should figure out that she's consistently underestimating and adjust, perhaps, or whatever. Okay. Now, going back to the tumor example, the statistics for these studies are based on binary outcome data. You know, the tumors did or did not metastasize. And so this gives us right away a difference between simply having the results for the studies and having the data, the outcomes on which the studies were based. Because if you had the outcomes and the intersection of tumors that satisfied both of these were there, you would be able to figure out statistics about the intersection, perhaps. Okay. So there is a really important difference between just having estimates and having the actual data. Now, if you're given the expectations only, you can choose values for the different regions here. So that the expectations are preserved for your two studies, your two sets, S1 and S2. And in general, if you have a whole collection of sets, C, and you have estimates for each set on the probability of an event in that set, then you can build, you can build a predictor which is multi-accurate with respect to a collection of sets, meaning that the predictions that you create will on average always match the expectations for the set. So you'll always match the expectations for the set. Of course, I'm wildly ignoring, sampling error and stuff like that, and everything that I say has to be adjusted to small noisy errors, but forget that. So multi-accuracy, I first saw, I think it was first proposed by Aber Johnson, Kim Reingold, and Rothblum, and it was a fairness goal, and it's kind of a warm-up for a stronger goal that we'll get to in a bit. But this is interesting, and you don't need training data for it. You can just go based on the estimates. So notice that if you have a pretty large collection of data points, samples, training data, and the sets are large, S1, S2, and so on are large, then your samples will give you good estimates for the expectation for these sets. You've got enough samples from each of the sets if you have enough data points. And the sets are not required to be disjoint, just like in this picture. So while to get multi-accuracy, all you need are the expectations, if you have training data, then you can compute approximations to these expectations, and you can get multi-accuracy. And I love their algorithm, and I really wish I had time to show it, but I don't. Now, you can have a multi-accurate predictor or scoring function, but there are many multi-accurate scores to choose from, functions that you could choose from, and the expectation for the intersection is not nailed down in general by multi-accuracy. And so getting back to this recidivism prediction or tumor prediction, I don't know what I would do if I see that this expectation is not nailed down at all. And the outcome also may not be calibrated. Okay. Now, if we think about the loan example for a minute, and we try to think about discrimination in lending, and because now people are involved, it's a little bit different than when we just are talking about tumors. You want a large, rich collection of sets. And Claude Steele, in his book Whistling Vivaldi, writes, there exists no group on earth that is not negatively stereotyped in some way. The old, the young, northerners, southerners, WASPs, computer whiz kids, Californians, and so forth. So this brings up the question, how do you choose which sets you want to have in your group, in your collection of sets for your multi-accurate predictor or what will be multi-calibrated? So, minimally, you would like your policies to be consistent with the expected repayment rates for each group. And the expectations now are determined by, I don't know why, but sorry. Skip that bullet, just forget it. Let's go on to the next slide. So the which groups question. Which groups should you include? Who decides? So should the culturally dominant be the group that's deciding which sets to include for multi-accuracy? Should we rely on the oppressed to stick up for themselves here and say, hey, you should treat us fairly, you should include us in this set? And in a groundbreaking 1994 paper, Jost and Banerjee argue that members of negatively stereotyped groups or members of an oppressed group tend to internalize the negative stereotypes and don't even necessarily realize that they ought to be asking for better treatment. Or perhaps I should say that we ought to be asking for better treatment. So there's evidence to show that individuals generate beliefs about themselves and stereotypes about social groups in such a way that existing situations are justified. So we try to explain to ourselves why this is okay rather than saying, wait, this isn't okay. Objectively, this is not okay. So what's the point of bringing this up? Complexity theory rocks. So the approach taken in Aber-Johnson et al. Is to just say, hey, let's look at something that will protect all groups that are defined by small circuits. Now, the intuition here is that this will probably capture, or it might capture, we hope, all historically disadvantaged groups. It does require, though, that the data will be sufficiently rich to permit identification of membership in this group, right? So it has to be that based on the data, you can tell whether someone is in the set or not. Otherwise, it's not helpful. Okay, so as I mentioned, you can actually achieve multi-accuracy. The complexity can be hard. It's related to the complexity of creating the multi-accurate scoring function will depend on the hardness of agnostically learning this collection of sets. But you can build the function, modulo that, you can have an efficient predictor. And the extra condition that they have is multi-calibration, that a scoring function is calibrated on each set in the collection simultaneously. So you're accurate in expectation not only over all sets in the collection, but within each set, if we look at the slice of people that were assigned the value v, you're accurate in expectation over those as well. So the first collection is fixed in advance, and sort of standard machine learning techniques let you do this. The second one is determined adaptively, and they use differential privacy to protect in the adaptive data analysis to do this. Now, the collection of sets is absolutely critical here. And as I said, the hope is to capture sort of, for each task-specific semantically significant differences among people. But the data that you have can be differentially expressive. So for example, think about AP classes. in a wealthy school district, there are AP classes, and college-capable students have a chance to prove this by taking AP scores, and in their weighted GPAs, they could even then get a weighted grade point average that is above 4.0 because you get an extra point for the AP classes. But in an impoverished school district, you simply don't have that information. There aren't AP classes, and there's no way for these, based on grades for these college-capable students of demonstrating this. So what we have here is that the data are differentially expressive. What you have is just not enough. And that's a really big issue. We think we have some way of at least a one-sided test for this, but as I said, this is work in progress. Now, really briefly, and tell me when I have 2 minutes left. So this led to a study. I mean, we started studying ranking. And the question is, why would we study ranking? So first of all, you want to rank fairly. Ranking is at the heart of triage. You've got an emergency situation, you have to make decisions and treat people right away. Okay. Ranking is often the underlying impetus for the scoring function, right? You want to score everybody and take it, people. So by studying ranking, it actually helped to inform us of what we want from a scoring function. Also, some affirmative action strategies are a sort of merge sort. That is, you partition the population either, let's say, according to high schools, as is done in Texas and in California, or in Romer's theory about justice, you can stratify students by the education level of the mother. And then you have a method of ranking students within each of these strata, and then you take the top X% from each group. And so this is what the UC system does and University of Texas system does. Okay. And finally, if you're an experienced clinician and you're given ranking information, then you can sort of translate that into a score by yourself. If someone tells you this person is in the top 10% of the risk category, you know something about how likely they are. And that actually brings up a general theorem which says that if you have fair ranking and binary historical outcomes data, you can actually create a fair scoring function. But I don't have time, I think, to talk about exactly what we do here. But we defined two hierarchies. They're short hierarchies, but they're two hierarchies. One of them is based on thinking about treatment of pairs of sets and what we want to avoid. So we have minimal requirements, stronger requirements, and yet stronger requirements, and that's our first hierarchy. The second one is a notion of evidence consistency. So if you have a ranking and you want that your ranking will be consistent with the rank induced by a scoring function that satisfies certain properties. So scoring functions immediately give you rankings. You just rank according to the score. So what are the properties that you would want? You look at increasing accuracy requirements in the scoring function. And we match up the levels in the hierarchy, and in fact, the top levels are equivalent. And the top level can be achieved by ranking to be consistent with any multi-calibrated scoring function. So here, multi-calibration came in again in a different impetus. And it seems, and we can sort of, we're working on formalizing this, but it seems that any kind of stronger requirements than the ones that we've laid out will arise in the choice of sets, not in the treatment of the sets that you have specified. So an example is that AP scoring not being visible in the sets. Okay, last slide. Perspective on individual probabilities. So we're exploring a possible analogy to indistinguishability. If positive and negative examples are computationally indistinguishable, then our community tends to think it's okay to assign a probability according to the distribution. In some sense, we believe this is the best we can do. That faced with computational indistinguishability, we're stuck. So maybe we can think analogously, and we can say, if the set C is really rich, so we've managed to get a set that is not differentially expressive, maybe analogously it's legitimate to treat any C multi-calibrated prediction function as if it were the truth. Because in some sense we're saying, hey, this is a really rich class of things, of sets. These sets can't manage to separate people, so this is the best we can do. So that's what we're exploring now, and this is why this is work in progress. Stop. Okay, thanks. Frauke.
Thank you, Cynthia. This is a very inspiring talk. Starting from the back end with one question. You mentioned, I forgot the name of one of the psychologists, I believe, for the clinicians, when you said they're learning adaptively what's relevant, right? That sort of, or what they take in.
This is the Barbara Underwood, the law.
Yeah.
Law.
And so I was wondering, I mean, with the multi-calibration, you still are constrained
Yes.
by the information you have.
Right.
And I guess one of the challenges, what gets into that collection, right? And is there something in what you explored in the multi-calibration that would hint at additional data that you might need, or where sets are not, like they might be slightly distinguishable, or where you feel like here's a lack of information, you know what I mean?
So I mentioned the problem of differential expressiveness, and I said, work in progress. we have, I think, at least a one-sided test for this. So when it says something is wrong here, something is wrong.
Okay.
Hopefully we can, at least information theoretically, make it two-sided. So that's the direction we're pursuing for answering that question.
Okay, cool.
Yes.
Have you any comment on the issues in redistricting, in gerrymandering versus fixing the mechanism and looking at what comes out that are currently before the courts?
Aaron, do you have a comment on fairness gerrymandering?
Not in that sort of word, I don't think.
Aaron has a paper together with Kearns and Neil
Okay,
and Wu. Anyway, no, I don't have.
There is a statistician's brief which doesn't help at the moment, because while it makes an important point, it totally confuses the few issues that they've been trying to grapple with. By saying that judging the outcome is not enough, and giving an example. I've only read an article based on it, not the brief itself.
My exposure to that question is through a couple of talks by Moon Duchin, who has done really interesting algorithmic work, but I can't speak to the issue you're asking about.
Okay.
Yes?
Maybe this is related to Franco's question, but so if you discover a new category, you want to enrich your set C, is that possible sort of as a, after that, I mean, so.
Right. So
Like,
you'd have to.
growing over time or something.
So I'm sorry, you're asking if you can rebuild the algorithm?
I mean,
I don't see why not.
yeah, I guess I mean, because I didn't have time to see like the actual method, but I was sort of wondering if you had imagined that you start learning about more cases of I'm an alien, I come to the,
Right.
I don't know about which categories you have experienced discrimination. I learn every day about more and more, and I build my circuit, class C over time.
So, yes, you can, but I think that the hope is that by saying, well, we're going to do this for all small circuits, that we won't need to do that. Now, I understand there's a big complexity issue in doing something for all small circuits. And so the results are existential in this case rather than efficient.
Right.
But I don't see why you can't redo it. There's no reason why you couldn't redo it.
It's like a way forward, a way to make
Yeah.
it more.
Yeah. So in the actual construction of the algorithm, in some sense, the first thing, you pick a set and you arrange probabilities so that that set is happy. And then you now look for another set that's unhappy in a really typical way. And then there's a potential function argument that says you don't have to do this very often. So it may well be the case that for many new sets that you find, it wouldn't even affect the circuit. The circuit you have is just fine. You don't have to, there's not a piece of the circuit that's built for every set in the collection. You can get by with way fewer. Yes, Frauke.
I think I saw Adam's hand up, but if I can also.
Go. I'll hold my question for offline.
Back to the individual probabilities.
Yeah.
Right? So for all possible sets, well, within a set, indistinguishable, and then you feel comfortable using the probability. That was what you said at the end. That's the best we can do, right?
So I think it's an overstatement to say I feel comfortable,
Okay.
but
that's the best we can do.
we are thinking about feeling comfortable with this.
Yeah, okay. So how is this different than sort of initially when you start out and say, I have, a set of covariates, a predicted probability, that of course only works in the distribution and in expectation, but is still for an individual.
So one of the things that's going on here is you're doing this, you're solving a set of simultaneous equations, right? So you don't just have one collection of features and you're measuring people who are like that on those features and using their probabilities. You're gathering much richer information and you're solving for pieces. You're solving so that you get something that's consistent with all of the evidence that you've seen. And the evidence can involve groups that this person isn't even part of that contribute to the set of constraints.
Yeah, okay.
All right, let's take further questions offline and